My name is Camryn Young. It is July 25th, 2025, and this is my Genetics Unit 2 presentation on mapping demonstration. So this is the given information we have for this problem. We have 8 different forms of phenotypic offspring showing 8 different forms of either mutation or non-mutation. If you're seeing the plus signs, that shows a wild type or non-mutation event. And if we're seeing an A, B, or C, that shows a mutation on gene A, gene B, or gene C, respectively. Using this information, we are going to find the order that these genes are on the chromosome, and then also the distance of these genes from each other on the chromosome. One of the first things we're going to want to do is figure out the total number of offspring. So we add together all of these offspring and get 5,742 total offspring. Some additional information we want to know is the difference between non-crossover, double crossover, and single crossovers. So non-crossovers are the most frequently occurring in offspring because that homologous pair is going to always have one of those chromosomes that does not cross over. So those parental chromosomes are going to be the highest percentage. On the flip side, double crossover events are going to happen the least frequently because you need 2 simultaneous crossover events happening on a chromosome. This is the lowest percentage of occurrences, so the lowest percentage of offspring are going to therefore have double crossovers. On the other hand, single crossover events will have the most variation and be between that highest non-crossover percentage and below that parental non-crossover event, but above that double crossover event percentages. So if we put all of our information in a table here, we will see that plus and ABC both have the highest percentage of offspring, which show that they are both our non-crossover chromosomes. So old wild type and old mutations will be our 2 parental chromosomes. And then our double crossovers are 1.7% and 2.4% respectively, with the A++ and the plus BC crossovers will be double crossovers, with everything else being a single crossover event. This helps us determine that both B and C genes, because they are together during a double crossover that occurs on either side of the chromosome, they must be the furthest apart from each other for these double crossovers to occur and affect them both. This means that gene A is therefore in the middle, and we have our order determined, which will either be CAB or BAC. In this example, we will be using BAC. The important thing is just that that A gene is in the middle. So if we take everything in the table and kind of switch it up a little bit, we are going to look at the recombination between B and A, the recombination between A and C, and the recombination between B and C to help determine their distance from each other. We calculate all the genes on the chromosomes where A and B are different from where they would be on a parental gene, which gives us a total of 18.5% of offspring. A difference of recombination between A and C from the parental genes will yield a total of 38.7% of the total offspring. And then a recombination event between B and C will show a total of 48.8% of the total offspring will have a recombination. This means that 1% of recombination is equal to 1 mapping unit. So that means the distance between B and A genes is 18.5 mapping units. The distance between A and C is 38.7 mapping units. And the expected distance between B and C is 57.2 mapping units, because if we add those two, we should get the total of 57. However, the actual number we receive is 48.8 mapping units. This is a large difference of 8.4 mapping units, but we're going to look at the coefficient of coincidence and the calculation of interference to conclude whether or not this is accurate. So looking at the expected double crossovers, we get the percentages of each crossover to get 0.0716. We can multiply that by the total offspring and know that we are supposed to get around 411 expected double crossover offspring, but the observed ones we have are only 240. That gives us a coefficient of coincidence of 58.4. That means we're only seeing 58.4% of all possible double crossovers. The calculation of interference is 1 minus 0.584 because of that percentage, and we get 416, which means that 41.6 of expected double crossovers are missing or not visible. That means that this large calculation of interference and this large coefficient of coincidence falls in line with that big difference between expected and total. So it shows an accurate final map of the chromosome, with BAC being the total order, with genes B and A being 8.5 mapping units apart, A and C being 38.7 mapping units apart, and B and C being 48.8 mapping units apart. Thank you very much.